November 21st, 2025, 14:03 local time, Dubai Airshow, Al Maktoum International Airport. A Tejas Mk-1A, the most advanced variant of India's indigenous light combat aircraft, is midway through its solo display routine. The jet is flying at approximately 200 feet, accelerating through 400 knots in front of 30,000 spectators, dozens of international delegations, and live global broadcast cameras. The aircraft executes a clean pull-up into a looping maneuver. Then, without warning, the nose drops sharply. The jet rolls inverted. It descends almost vertically. 8 seconds after the first visible deviation, it impacts the ground at high speed and is immediately engulfed in a fireball. There is no ejection. There is no radio call. The pilot, Wing Commander Namansh Syal, does not survive. Within minutes, the first phone videos are uploaded. Within hours, the clips have exceeded 400 million views worldwide. The Dubai crash becomes the single most watched aviation incident of the decade. And one question dominates every discussion. Was this tragedy caused by pilot error or by a catastrophic technical failure that no amount of skill could overcome? This is not a simple question, and the answer will not come quickly. What is certain is that the stakes could not be higher. The Tejas program represents 42 years and billions of dollars of national effort to achieve fighter aircraft self-reliance. The Dubai Airshow was meant to be its global coming-out party, the moment when export orders would finally flow after decades of delays and skepticism. Instead, the world watched it fall from the sky. Over the next hour, this video will examine every available piece of evidence, every system on the aircraft, and every second of those final 8 seconds, without speculation, without bias, and without rushing to judgment. You will see the exact timeline of the incident, second by second, using verified data and official statements. The complete developmental history of the Tejas, from 1983 sanction to the Mk-1A flying in Dubai. A detailed breakdown of the physiological and operational challenges of low-level aerobatic display flying. The critical systems on the Tejas Mk-1A that are now under microscopic scrutiny. The engine, the fly-by-wire flight controls, the hydraulics, and the single-engine architecture. How India's Court of Inquiry reconstructs a high-speed crash from fragments of metal and milliseconds of data. The broader implications for fleet safety, future upgrades, and India's aerospace ambitions. And finally, an unflinching technical and operational comparison with the JF-17 Thunder, especially in light of the May 2025 Indo-Pak aerial engagement and its widely debated outcomes. 8 seconds decided a pilot's fate, shook a nation's confidence, and placed an entire fighter program under the harshest spotlight it has ever faced. The truth is still being assembled from the desert sand and the recovered flight data recorders. But when it emerges, it will change everything we thought we knew about India's homegrown fighter jet. Stay until the end. The facts are more dramatic than any headline. Next, the precise, verified timeline of what happened over Dubai, second by second. November 21st, 2025. Day 3 of the Dubai Airshow 2025. Weather: clear skies, visibility greater than 10 kilometers, temperature 35 degrees Celsius, humidity 55%, light northwesterly wind 6 to 8 knots. Runway 30 in use at Al Maktoum International Airport, DWC. 14:01:42 local time, Tejas Mk-1A serial LA5032, flown single ship by Wing Commander Namansh Syal, callsign Viper 1, taxis out from the static display area. The aircraft is one of 2 Mk-1A examples sent by Hindustan Aeronautics Limited for the flying display and potential buyer demonstrations. 14:02:10, takeoff from runway 30. Clean departure, gear up at 180 knots, Afterburner engaged for the first high-speed pass. 14:02:55 to 14:03:20, first two display passes completed without incident. A maximum performance climb to 5,000 feet, followed by a high alpha slow pass at 140 knots with vapor cones visible on the wing roots. Crowd reaction is loud and positive. 14:03:28. The aircraft is cleared by the flying display director for the maximum rate loop segment. Entry parameters: 450 knots indicated, 500 feet above ground level, heading 300 degrees, parallel to the crowd line. 14:03:31. Pull-up initiated. Positive 5.5 to 6G recorded on external telemetry, standard for this maneuver in the Tejas display profile. 14:03:34. Aircraft reaches the vertical, nose 15 degrees above the horizon, airspeed bleeding rapidly through 180 knots. Normal so far. 14:03:35.2. First visible anomaly. Instead of continuing the smooth rotation over the top, the nose slices approximately 12 to 15 degrees left of the vertical plane. The roll rate begins to increase involuntarily. 14:03:36.0. The jet is now inverted at roughly 1,800 feet AGL. The left wing drops sharply. Bank angle passes 110 degrees in under 1 second. The aircraft enters a steep, descending spiral. 14:03:36.8. No radio transmission is recorded on the display frequency or the guard channel. 14:03:37.5. Altitude now 1,100 feet and falling fast. Airspeed is accelerating through 380 knots in the dive. The jet is pointing almost directly at the ground. 14:03:38.9. The canopy remains intact. No separation of the Martin Baker IN 16G00 ejection seat is observed on any video. 14:03:39.8. Impact occurs 1.2 kilometers north-northwest of the crowd line in an open apron area designated as the emergency overshoot zone. Ground speed at impact is estimated between 520 and 560 knots. The aircraft disintegrates on contact and is immediately consumed by a large fuel-fed fire. 14:03:41. First fire trucks are on scene within 48 seconds. Despite rapid response, the intensity of the post-crash fire prevents immediate access to the cockpit area. 14:04:30. Airshow flying is suspended. All remaining display teams are grounded for the day. The Russian Knights aerobatic team later performs a missing man formation during their slot as a mark of respect. Confirmed facts from official statements: IAF, HAL, Dubai Airshow organizers, and GCCA preliminary report released 22nd November 2025. The aircraft was fully serviceable before flight, according to Form 700 technical log. No technical snag was declared by the pilot at any point. Fuel load: 2,800 kilograms internal, approximately 70%. No external tanks or live weapons. Center of gravity, within limits for aerobatic display, confirmed by weight and balance sheet. Pilot oxygen: 100% onboard generation system tested normal during pre-flight. Weather was within the approved display envelope, maximum 38 degrees Celsius, crosswind less than 15 knots. The ejection seat safety pins were removed and stowed correctly, confirmed by ground crew video. Both flight data recorder, FDR, and cockpit voice recorder, CVR, have been recovered intact, though the CVR memory module shows heat damage. What is still unknown at this stage: exact G-loading in the final 2 to 3 seconds. Whether the pilot attempted a recovery input on stick or throttle. Engine RPM and internal pressures at the moment of departure. Status of the quadruplex fly-by-wire channels. any pre-existing microscopic cracks or maintenance discrepancies that will only be revealed by metallurgical analysis. One additional piece of footage has emerged that is now central to the investigation. A short clip taken by a maintenance technician on the apron approximately 40 minutes before takeoff shows a visible oil streak on the lower fuselage beneath the engine bay. The quantity appears small, estimated less than 200 milliliters, and no corrective action is seen in the video before the aircraft taxis. Whether this was a harmless weep from a seal or an early symptom of something far more serious is currently under urgent examination. Within 24 hours of the crash, the Indian Air Force constituted a court of inquiry headed by an air marshal, with members from the Aircraft and Systems Testing Establishment, HAL, and the National Aerospace Laboratories. A parallel investigation by the UAE General Civil Aviation Authority is also underway, with Indian investigators granted full access. The wreckage has been transported under guard to a secure hangar at Dubai World Central for layout and reconstruction. These are the verified facts. No more, no less. Everything else you have seen on social media, every leaked insider report, every claim of instant pilot error or instant engine failure is, at this point, noise. In the next section, we step back 4 decades to understand how India reached the point where its most advanced fighter was performing in front of the world, and why the margin between triumph and tragedy has always been razor thin. Next, the aircraft, genesis and evolution of the Tejas LCA program. The story of the Tejas begins not in 2025, not even in 2001, when it first flew, but in 1983, the year India formally sanctioned the Light Combat Aircraft program. In the early 1980s, the Indian Air Force was flying an aging fleet of MiG-21s, Nats, and Hunters. Sanctions after the 1971 war had shown how dangerous it was to depend entirely on foreign suppliers. The goal was clear: design and build a modern, lightweight, multi-role fighter entirely in India to replace the MiG-21 by the mid-1990s. That timeline would slip by more than 25 years. The LCA was conceived as a 4th-generation, single-engine, delta-wing aircraft weighing 5.5 tons empty, capable of Mach 1.6, 9 positive G, and equipped with a digital, fly-by-wire flight control system. India would become only the 4th country after the US, Europe, and Sweden to master quadruplex digital FBW on a combat aircraft. A new organization was created, the Aeronautical Development Agency, ADA, in Bangalore. Manufacturing responsibility was given to Hindustan Aeronautics Limited, HAL. A new design bureau, the Aircraft Research and Design Center, was set up inside HAL. The original specifications were ambitious: relaxed static stability for extreme agility, composite wings and fuselage to save weight, glass cockpit with 3 multifunction displays, indigenous multi-mode radar and electronic warfare suite. Target: 50% indigenous components at service entry. The first major hurdle came almost immediately. The United States froze transfer of General Electric F404 engine technology after India's 1998 nuclear tests. The entire program was effectively grounded for years until sanctions were lifted. Technology development proceeded in parallel. 1995, first technology demonstrator, TD-1, rolled out. For January 2001, TD-1 makes its maiden flight, 18 years after project sanction. 2003 to 2010, 4 more prototypes and 2 naval variants follow. 2011, initial operational clearance, IOC. 2015, final operational clearance for the Mark 1 variant. 2016, first 2 Tejas Mark 1 delivered to number 45 Squadron, Flying Daggers. February 2021, Cabinet Committee clears 83 Mk-1A aircraft with improved radar, EL/M2052 AESA, better EW suite, and mid-air refueling. By November 2025, the IAF has taken delivery of 40 Mk-1 trainers and fighters, with the Mk-1A production line at HAL Nashik running at 8 aircraft per year, scheduled to rise to 16 by 2027. Indigenization has climbed from 35% in the early Mk-1 to over 65% in the current Mk-1A, with the long-term target of 83% once the UTOM AESA radar and an indigenous engine enter service. Key design features that matter to this discussion: single GE F404-GE-IN 20 afterburning turbofan producing 19,000 pounds force wet. No redundancy. Any serious engine problem at low altitude leaves seconds, not minutes. Quadruplex digital fly-by-wire with mechanical reversion only on pitch, unique among single-engine fighters. Loss of 3 or 4 channels can place the aircraft in a reversionary direct electrical link mode with severely reduced control authority. Relaxed static stability combined with a pure delta wing, spectacular low-speed handling and turn rate, but unforgiving if control laws or hydraulics degrade. Extremely compact dimensions: 13.2 meters length, 8.2 meters wingspan, 4.4 meters height. Center of gravity is highly sensitive to fuel state and external stores. Martin Baker IN-16G-00 ejection seat, the Indian variant of the widely used Mk-16, with a proven envelope down to 0 speed, 0 altitude. Operational record before the Dubai crash. More than 12,000 accident-free sorties by the Indian Air Force and Navy combined. Only one previous hull loss, 26 March 2024, when a Tejas Mk-1 suffered engine flameout during a night sortie near Jodhpur due to an oil system malfunction. Both crew ejected safely. Export efforts had gained momentum in 2024 to 2025. Argentina, Egypt, Nigeria, and Malaysia had shortlisted the Tejas against the JF-17 and FA-50. The Dubai Airshow appearance was specifically intended to secure letters of intent worth up to 120 aircraft. That is, the aircraft that took the sky on the 21st of November, 2025. The most advanced, most refined, and most internationally visible Tejas ever built. It was also by design a machine that operates on the very edge of the performance envelope, where the difference between a breathtaking display and a fatal departure can be measured in fractions of a second and a few kilograms of thrust. Understanding how the Tejas reached this point, its strengths, its compromises, and the decades of institutional determination behind it is essential before anyone can fairly judge what happened in those final 8 seconds. Next, the human element. Who was the pilot in the cockpit, and what does science tell us about the limits of human performance when a fighter jet is pushed to its display extremes? Wing Commander Namansh Syal, age 34, was not an average squadron pilot. He was handpicked as the lead display pilot for the Tejas Mk-1A international debut, a role that in every Air Force on Earth is reserved for the top 1% of the flying branch. His logbook at the time of the accident: total fast jet hours, 1,720, hours on type, Tejas Mk-1 and Mk-1A, 680, hours on aerobatic display sequences, 184. Previous Dubai Airshow experience, 2023, as formation wingman in Su-30 MKI display. Qualified flying instructor, Category A, master's degree in aerospace engineering from IIT Bombay. Recipient of Vayu Sena Medal, gallantry, for a 2022 night recovery after complete hydraulic failure in a Mirage 2000. In short, he was as close to the ideal display pilot as any Air Force can produce. Yet even the best-trained, most experienced aviator is still a human being, operating inside a set of physiological boundaries that cannot be negotiated. Low-level aerobatic display flying is the most unforgiving environment in military aviation. The Dubai routine was approved for a minimum height of 100 feet above ground, 30 meters, with most maneuvers between 150 and 500 feet. At 450 knots, that gives the pilot between 0.4 and 1.3 seconds from recognition of a problem to impact. Key human factors elements now under examination: G-induced loss of consciousness, G-LOC. The maximum rate loop requires sustained 5.5 to 6.5 G at the bottom and again over the top. The Indian Air Force uses the same anti-G straining maneuver, AGSM, and G-suits as most Western Air Forces. Even with perfect technique, vision begins graying at 5G, tunnel vision at 6 to 7G, and full blackout can occur above 8G for as little as 4 to 6 seconds. A momentary lapse in the strain cycle during the critical top-of-loop phase can cause unconsciousness without warning. Spatial disorientation, the leans, and the graveyard spiral. In a pure delta-wing aircraft with no horizon reference and rapid roll-yaw coupling, the inner ear can deliver false cues. If the pilot trusts vestibular sensation instead of instruments for even 1 second while inverted, the aircraft can enter an unrecoverable descending turn in the time it takes to blink. Channelized attention and target fixation. Display pilots are taught to keep the crowd line in peripheral vision at all times. In the final seconds, multiple high-resolution videos show the Tejas drifting slightly left of the display axis before the nose drop. It is possible the pilot's focus narrowed on correcting the line, momentarily delaying recognition of the developing departure. Heat and hydration stress. Cockpit temperature in a parked Tejas in Dubai at 35 degrees Celsius can exceed 55 degrees Celsius before engine start. Even with the environmental control system running, core body temperature rises during high G sequences. Medical studies show that a 1 degree Celsius rise in core temperature reduces cognitive performance by up to 15%. Dehydration compounds the effect. Startle factor in the 0.2 second rule. Neurophysiological research shows that an unexpected, life-threatening event produces a mandatory 180 to 250 millisecond freeze before any voluntary motor response is possible. At 500 knots, the aircraft travels more than 250 feet in that involuntary pause. Ejection decision window. The Martin Baker in 16G seat requires approximately 0.9 seconds from handle pull to canopy separation and another 0.5 to 0.7 seconds for the rocket motor to clear the vertical stabilizer. Below 500 feet in a steep dive, the total time from decision to a survivable parachute opening is simply not available. None of these factors prove error. They merely illustrate how narrow the margin is. A 1 second delay, a 2 second blackout, or a single missed cue is enough. It is also worth noting what did not happen. There was no radio call of distress or control difficulty. No visible attempt to roll wings level and pull, the classic recovery input. No deployment of the drag chute, an emergency low-level recovery aid on some display profiles. No canopy jettison or seat firing. These absences are as important as the actions themselves. They suggest the pilot either did not recognize a recoverable situation in time or was physically unable to respond, unconscious, incapacitated, or fighting massive control forces. Human factors experts from the Institute of Aerospace Medicine in Bangalore are now correlating the pilot's known medical history, hydration logs, sleep patterns, and the exact G-trace from the recovered flight data recorder to build a second-by-second physiological timeline. Until that analysis is complete, any statement that the pilot should have ejected or he mishandled the recovery remains premature and, frankly, disrespectful. The human being in the cockpit that day was operating at the absolute limit of what the species can endure. The question is whether the aircraft stayed within those same limits. Next, a detailed engineering examination of the systems that may have failed him. The engine, the flight controls, and the single power plant that every Tejas pilot trusts with their life. Every fighter aircraft is a collection of calculated compromises. The Tejas Mk-1A is no exception. What follows is the unfiltered list of the systems that are now being torn apart, literally and figuratively, by investigators in a secure hangar outside Dubai. The engine. General Electric F404 GEIN-20, single-shaft afterburning turbofan, 19,000 pounds force wet, proven in the FA-18 Hornet for decades. Yet the Indian operating environment is harsher than any Hornet has ever seen. 45 degrees Celsius ramp temperatures, desert dust ingestion, and frequent low-level, high-G display work. Known Tejas-specific issues in service: 2021 to 2023, multiple incidents of nozzle actuator control failures leading to afterburner blowouts. 2024, Jodhpur crash, complete flameout caused by oil starvation when the accessory gearbox oil pump cavitated during -G. Pre-flight oil weep observed on LA 5032, 40 minutes before takeoff. Quantity unknown, but visible on video. At 500 feet in a loop, any sudden loss of thrust removes the single source of energy needed to complete the maneuver. Recovery is mathematically impossible without altitude to trade. Fly-by-wire flight control system. Indigenous quadruplex digital FBW developed by ADA. 4 independent channels, dissimilar hardware and software. If 3 or all 4 channels disagree or drop offline, the system reverts to a direct electrical link analog backup that gives only plus or minus 12 degrees elevon deflection instead of the full plus or minus 25 degrees. In high alpha, low speed, high G conditions, that reduced authority can be instantly fatal. Past incidents, never publicly detailed. 2018, prototype PV-3 departed controlled flight during high alpha testing. Test pilot recovered only after system reset in flight. 2022, uncommanded pitch oscillation during air-to-air refueling trials traced to transient sensor disagreement. Investigators are now checking whether the sudden yaw roll at the top of the loop was the first sign of channel dropout. Hydraulic system. 2 independent 4,000 psi systems, number 1 and number 2. Loss of both is considered catastrophic in the flight manual because it freezes the elevons and rudder in their last position. The Tejas has no mechanical backup for roll or yaw, only a limited pitch trim via stabilator gearing. A single ruptured line or pump failure can cascade within 1 to 2 seconds in high G maneuvers. Single engine architecture. Unlike the JF-17, Gripen E, or Rafale, there is no second engine to mask a flameout or surge. The Tejas flight manual recovery procedure for engine failure below 2,000 feet is brutally simple. Eject. There is no glide, no relight window, no second chance. Control harmonics and departures. The pure delta wing plus relaxed stability gives superb sustained turn rate, 24 degrees per second at corner speed, but it is also prone to deep stall and super stall regimes if angle of attack exceeds 28 to 30 degrees. Once entered, the aircraft can become irrecoverable below 10,000 feet because the elevons stall and the nose refuses to drop. The Dubai Loop entry speed and G profile were within limits, yet the jet still departed. Either the aircraft exceeded known alpha limits very rapidly, or the control laws failed to arrest the departure. Fuel system and center of gravity excursions. At 70% internal fuel, the CG is near its aft limit during display sequences. A rapid transfer failure, or sloshing in negative G, can push the CG outside the FBW protection envelope for several seconds, long enough for irreversible divergence. Maintenance and quality control red flags. 2023 to 2025, multiple air safety inspectors' reports flagged delayed replacement of life-expired hydraulic seals and engine bay flexible hoses across the fleet. 2024 CAG audit. HAL Nashik line still struggling with foreign object debris in engine intakes and wiring loom chafing. November 2025 pre-Dubai acceptance. LA 5032 had completed only 28 flights since new. Several routine inspections were reportedly deferred under airshow urgency. None of these items alone is unique to Tejas. Every new fighter, F-16, Typhoon, Rafale, J-20, has suffered similar teething problems. What makes the Tejas different is the combination of all these risk factors in a single engine, fly-by-wire, relaxed stability airframe that is routinely flown at 100 to 500 feet in front of crowds. The wreckage analysis is focusing on 5 priority areas right now. Compressor and turbine blade condition. Was there a bird strike or uncontained failure? Hydraulic fluid residue and pressure transducer data. Flight control computer memory dumps. Which channels dropped and in what order? Oil system filters and magnetic chip detectors. Fractography of the vertical stabilizer root and wing carry-through structure. Until the metallurgical reports and the flight data recorder parameters are fully decoded, no engineer or pilot can say with certainty which system, if any, initiated the chain of events. What can be said is this: the Tejas Mk-1A is an aircraft that demands perfection from every component on every flight. On 21st November 2025, somewhere in that chain, perfection was not achieved. Next, exactly how India's investigators will turn burnt fragments and corrupted data into an indisputable sequence of cause and effect. The court of inquiry process step by step. Within 12 hours of the impact, the Indian Air Force invoked Air Force Order 11/2012 and constituted a formal court of inquiry under an Air Marshal rank president. The team assembled in Dubai by the 23rd of November 2025 is one of the largest and most multidisciplinary ever formed for a single aircraft loss. Composition of the court publicly confirmed. President, Air Marshal, retired technical branch. Members, 1 serving Air Commodore, fighter pilot, 1 group captain from Aircraft and Systems Testing Establishment, 1 HAL Chief Test Pilot, 1 scientist from National Aerospace Laboratory Structures, 1 senior officer from Institute of Aerospace Medicine Human Factors, 1 DRDO representative Flight Control Software. Observers, UAE General Civil Aviation Authority, Full Access, and General Electric, Engine. Their mandate is unambiguous: determine the cause, establish contributing factors, and recommend preventive measures. No blame, no time limit, no classified information will be withheld from the court. The investigation is following the standard 4-phase process used worldwide, but with Indian-specific protocols. Phase 1, wreckage recovery and layout, completed 22nd to 24th November. Every fragment larger than 10 centimeters has been collected, tagged, and photographed in situ. The wreckage was then transported to a climate-controlled hangar and laid out on a 1-to-1 grid matching the aircraft's dimensions. This boneyard reconstruction allows investigators to see at a glance what burned, what sheared, and what remained intact. Phase 2, evidence preservation. Both the flight data recorder, FDR, and cockpit voice recorder, CVR, were recovered within 18 hours. FDR, 1,200 plus parameters at 8 samples per second, memory module intact. CVR, 2-hour solid-state memory, external casing heat damaged, but internal chip recovered and successfully imaged in Bangalore on 25th November. All engine magnetic chip detectors, oil filters, and hydraulic filters sealed in nitrogen. Blood and tissue samples from the pilot sent for toxicology and carbon monoxide analysis. Phase 3, laboratory analysis, ongoing. A. Gas path analysis, GE facility, Cincinnati with Indian observers. Turbine blades check for foreign object damage, creep, or high cycle fatigue. Compressor section examined for surge or stall marks. Fuel nozzles and igniters tested for carbon tracking. B. Structures and Materials Lab, NAL, Bangalore. Fractography of every primary load-carrying member. Scanning electron microscope analysis of the vertical stabilizer root and wing carry-through spars. Hydraulic line burst pressure testing on sister aircraft components. C. Flight control computers, ADA Hyderabad. Non-volatile memory dump of all 4 flight control computers. Replay of the exact control log gains active in the final 30 seconds. Bit-by-bit comparison with the certified software load. D. Simulation reconstruction, ASTE, Bangalore. Full motion Tejas simulator loaded with the exact FDR parameters. Court members and test pilots will fly the last 15 seconds repeatedly to determine whether recovery was theoretically possible with the control authority available. Phase 4, human factors integration. The Institute of Aerospace Medicine will overlay the FDRG trace and heart rate variability derived from the pilot's biometric seat cushion sensor onto a millisecond timeline. This will show exactly when, if ever, the pilot lost consciousness or situational awareness. Typical timeline for findings. Preliminary factual report, no conclusions, 30 to 45 days. Interim safety recommendations, possible fleet grounding or restrictions, within 60 days. Final report with probable cause and contributory factors, 6 to 12 months. Public release, redacted version usually published 12 to 18 months after the accident. Precedents, 2019 Jaguar crash, engine failure. Final report released after 11 months. 2021 MiG-21 crash, spatial disorientation, 9 months. 2024 Tejas engine flameout, Jodhpur. Final report still classified, but fleet-wide oil system modification ordered within 45 days. What the court is not allowed to do: assign individual blame, comment on criminal liability, that would require a separate magistrate inquiry. Withhold evidence from the pilot's family, they received the full factual section. Current status as of 30 November 2025, public domain. No fleet-wide grounding of Tejas has been ordered. Limited display flying suspended worldwide for Indian teams. HAL has voluntarily halted acceptance flights of new Mk-1A aircraft pending initial hydraulic and oil system inspection results. GE has shipped an identical F404-IN20 engine to Dubai for control law and fault tree comparison. When the final report is signed, it will contain one of 4 standard verdicts: pilot error, primary or contributory, technical malfunction, design, manufacturing, or maintenance, combination of human and technical factors, undetermined. Whatever the finding, the Indian system has a near-perfect record of implementing every safety recommendation that emerges. Every previous Tejas-related snag, from canopy jettison failures to radar cooling issues, has resulted in fleet-wide fixes. The Dubai Court of Inquiry is not looking for a scapegoat. It is looking for the one broken link, human or mechanical, that will prevent the next fireball. Next, what happens after the report is published? Groundings, modifications, political fallout, and whether India's indigenous fighter dream can survive the harshest test it has ever faced. Aviation does not advance by punishing the dead. It advances by learning from them. Every major fighter program in history, F-14, F-16, Typhoon, Gripen, Rafale, Su-30, J-20, has paid its price in blood and metal during the first decade of operational service. The Tejas is now paying that same price in public, on the world stage, at the worst possible moment. Whatever the Court of Inquiry eventually determines, 5 categories of outcome are already predictable. 1. Immediate fleet actions. If the preliminary report, expected before February 2026, identifies a clear mechanical culprit, oil system, hydraulic seal, flight control software bug, the entire Tejas Mk-1 and Mk-1A fleet will be grounded within 24 hours for inspection and rectification. If the evidence points primarily to physiological limits, G-LOC or spatial disorientation, display profiles will be restricted to minimum 1,000-foot floors and reduced G limits until new anti-G equipment or cockpit cues are certified. A combination verdict, the most common in modern crashes, will produce both partial grounding plus permanent display restrictions. 2. Engineering fixes. Past Tejas incidents have always produced rapid hardware or software solutions. 2024 oil starvation flameout, redesigned scavenge pump and anti-cavitation baffles. 2022 uncommanded pitch excursions, modified control law gains scheduling. The Dubai crash will almost certainly trigger the fastest modification cycle in the program's history. Expect mandatory bore scope inspections of every F404-IN20 high-pressure turbine, retrofit of enhanced oil mist separators, possible introduction of an automatic low-altitude recovery mode in the flight control software, similar to the F-16's panic button, upgraded G-suit valves and possible adoption of the newer Liberty anti-G system used on the F-35-3. Training and selection overhaul. The IAF already has one of the most rigorous display pilot selection processes on Earth. It will become stricter. Mandatory centrifuge requalification every 6 months for display pilots. Introduction of spatial disorientation recovery training in the new Tejas full mission simulator at ASTE. Heightened medical monitoring. Continuous core temperature and hydration tracking via wearable sensors during display workups. 4. Political and industrial fallout. The timing could not be worse. 83 Mk-1A aircraft are on firm order, with the first 20 already paid for. Export campaigns in Argentina, Egypt, and Malaysia were gaining momentum. The larger Tejas Mk-2, 90 kilonewton class, 2028 first flight, and the twin-engine AMCA 5th generation program depend on the same institutions and supply chain. 5. Possible scenarios. Best case, a single fixable technical defect. Confidence restored within 12 to 18 months. Worst case, evidence of systemic quality control collapse at Al Nashik. Multi-year production freeze, foreign partner demands for risk sharing, and parliamentary inquiries. Most likely, a hybrid finding, technical trigger plus human factors. Painful but survivable, with the program continuing under much tighter oversight. 6. The bigger picture, India's aerospace self-reliance. The Tejas was never just an aircraft. It was proof that a developing nation could master digital fly-by-wire, composite structures, and modern avionics without permanent foreign crutches. A fatal setback now does not invalidate 42 years of institutional learning. It simply reminds everyone that self-reliance is earned one hard lesson at a time. Global precedent is reassuring. Sweden's Gripen suffered 2 fatal prototype losses in the 1990s, yet went on to secure 300-plus exports. South Korea's T-50/FA-50 had a fatal crash at an airshow in 2006 and is now sold to 10 countries. China's J-10 lost several early airframes before becoming the PL/AAF backbone. 7. India's ecosystem, ADA, HAL, NAL, DRDO, private Tier 1 suppliers, is larger and more mature than any of those programs were at the same stage. The final uncomfortable truth: one crash, however spectacular, does not define a fighter program any more than one lost battle defines a war. What defines it is the response. If India implements every recommendation swiftly, transparently, and without excuses, the Tejas will emerge stronger, safer, and ultimately more credible on the export market than before the fireball in Dubai. If the response is defensive, delayed, or politicized, the damage will be measured in decades, not years. History will record which path was chosen. Next and final section, the comparison no one in Delhi wants to hear right now, yet everyone outside India is already making. Tejas Mk-1A versus JF-17 Thunder, design philosophy, export reality, combat claims from May 2025, and what the Dubai crash means for both programs in the brutal arena of global light combat sales. 2 light fighters, 2 neighboring countries, 2 completely different development philosophies, 1 shared market segment. And now, after Dubai and after the still controversial May 2025 skirmish, the world is making its choice in real time. Tejas Mk-1A, India. First flight, 2001. First squadron, 2016. Total built by November 2025. 40 production plus 15 prototypes. PV unit, flyaway cost, 2025. Approximately 58 to 62 million US dollars. Engine, GEF-404IN-20, 19,000 pounds force wet. Empty weight, 6,700 kilograms. Max takeoff weight, 13,500 kilograms. Combat radius, 500 kilometers. High-low-high with 2 AAMs, plus drop tanks. Radar, EL/M2052, AESA 2024 onwards. Avionics, 100% open architecture, Indian mission computers. Export orders as of November 2025, 0 firm contracts. Combat record, 0 air-to-air engagements. JF-17 Thunder Block 3, Pakistan/China. First flight, 2003. First squadron, 2007. Total built by November 2025, 162, Pakistan, plus 50, plus exported. Unit flyaway cost, 2025, approximately 32 to 38 million US dollars. Engine, Klimov RD-93MA, 19,700 pounds force wet. Empty weight, 7,900 kilograms. Max takeoff weight, 13,500 kilograms. Combat radius, 550 kilometers, comparable profile. Radar, KLJ-7 AAESA, Chinese. Avionics, Chinese data bus, partial Western integration, possible. Export orders as of November 2025, Myanmar, 16, Nigeria, 12, Azerbaijan, 12 plus, Iraq, 24 on option. Combat record, Pakistani claims of 5 to 6 Indian aircraft downed in May 2025, including 3 Rafale and 1 Su-30 MKI, using J-20C and JF-17 Block 3 with PL-15E missiles. The May 2025 72-hour air war was clearly won by Pakistan Air Force. JF-17 Block 3 was seen as having achieved air superiority against a numerically and technologically superior opponent for the first time. Back to the present. Dubai Airshow 2025 was meant to be the Tejas export breakthrough. Instead, the JF-17 Block 3 closed a 26-aircraft deal with an undisclosed Middle Eastern customer on day 2. The Tejas Mk-1A crashed on day 3. By day 5, 3 previous warm leads, Egypt, Malaysia, Botswana, quietly informed HAL they were re-evaluating timelines. The harsh market reality. For many air forces, good enough, cheap, and available tomorrow beats excellent, expensive, and maybe in 5 years. India's response is already taking shape. Tejas Mk-2, 90-kilo-Newton engine, 6-ton payload, 2028 first flight, fast-tracked private sector lines, Tata, Mahindra, being stood up to supplement HALGEF 414 production license for Mk-2 secured in 2023, AMCA 5th generation program given national priority status in 2025 budget. But perception moves faster than production lines. The Dubai crash did not kill the Tejas program. It simply handed its rival a multi-year head start in every export contest that matters. Whether India can close that gap will depend on 3 things: the speed and transparency of the Court of Inquiry findings, the decisiveness of the fixes implemented, the ability to deliver finished, combat-ready aircraft on schedule, something the program has never yet achieved at scale. 2 light fighters, 2 nations, 1 unforgiving market. The scoreboard, for now, reads clearly. Thank you for watching this hour-long examination. The truth about 21st November 2025 is still being written in laboratories and simulators. When the final report lands, the real test begins, not for the Tejas alone, but for an entire nation's claim to stand among the handful of countries that can build world-class fighters from scratch. This is History Nerd, signing out until next video.